We have then the last presentation with 2 chapters, 13 and 14, Cost and Studies on SFTB by Torole Olsen. And after this, we will have some questions. Please pose your questions in your Q&A or in the chat, and then we will try to answer all the questions from the audience. Torole, please, you can share your screen.
Thank you, David. Costs of the SFTB is not so simple. It could have been simple if we had a number like this, but we don't, unfortunately. But we do have a lot of experience with relative costs, and I will try to explain what we know from many studies. Most of the numerical values are in terms of money, but I would like to add that also the cost in terms of environment is important. I have sketched a bridge on the right picture here. It may not be the most beautiful bridge you've seen, but many people like lakes the way they are and crossings, and that's one of the environmental costs we need to consider. There are other things in the environmental part. In general, the SFTB competes with ferries, bridges, floating bridges, immersed tunnels, subsea tunnels, and the long road around, if possible. But predominantly, it is the ferries that is the used solution. And we know that ferries requires a lot more fuel than the equivalent of all the cars that it can carry, if the cars could drive the same distance. And this, of course, is because a propeller is much less efficient than a tire on firm ground. Many years ago, we calculated that the fuel consumption was 10 times as high for a ferry. But modern ferries may be different. And then you have emissions of all sorts of gases that shows that the SFTB is very, very favorable. And in addition, you have time, availability, and accidents. We know that it's often a race in our country to reach ferries. So accidents and the availability and time are important factors. The cost depends on many things, among others, length of the crossing, of course, number of lines, traffic loads, support systems and structure, environmental conditions, currents and waves, connection to shore, construction method, installation, towing, financing, and others. Large structures need a graving dock to build at last a part of the structure. This graving dock requires space and represents a major cost. Construction is a major cost of the SFTB. Gordon showed you the construction of the Femern immersed tunnel, and the impression is that that is not very inexpensive. If you have smaller structures, you may do with smaller expenses. You can use a ship dock if suitable. You can use an ordinary dock with subsequent wheeling to a barge for submergence. You can lift elements you can build on a barge for subsequent submergence, built by elements, lifted together by crane, and you can use purpose-built structures. Obviously, the facility of the contract is important and for the execution of the project and also for the design. Therefore, integration of design and construction is very important. This picture you've seen before, this is a relatively inexpensive and simple way of construction. This is a ship dry dock. Up left is another ship dry dock. This is the construction of a sea bath in Oslo. Norway has 100,000 kilometer coastline, if you include islands, but even then we built sea baths. We use various techniques, and as you see, it is very popular. These are marine concrete structures in general. The one in the middle is built on an ordinary dock and lifted out. It weighed 250 tons, lifted by a sea crane, as you can see. This is a restaurant that was built on a barge and then lifted in place. It's a restaurant underwater, and this is how it looks from the inside. Now, for the SFTB, if you compare SFTBs cost-wise as a function of length and compare them with the suspension bridge, not surprisingly, you have an asymptotic price escalation with length for a suspension bridge. For the SFTB, it is maybe more or less constant, maybe even going down a little bit. To the right here, you see it's a range. You have suspension bridges, you have submerged floating tunnels, and you have immersed suspension bridges. That is a suspension bridge sitting on floating pontoons. Bear in mind that the longest ordinary bridge today is 2,000 meters. You are approaching some asymptotic value for the bridge. Here we have plotted costs of floating bridges that are built. They are down here, these two. Floating bridges studies. These are the empty squares, and SFTB studies are the empty circles. The reason for the gap here is that these two floating bridges are single lane bridges. These are double lined. And this is an important illustration of relative costs. Firstly, you see that tube construction is a major part of the cost. To the right here is the tether stabilized, and to the left is the pontoon stabilized SFTB. So you have some differences in the way you stabilize the structure. So this is something to have in mind when you are planning an SFTB. To further expand on the costs. We have tried to plot uncertainties, risk elements around the different costs. These figures are in the report. By the way, the report, if you're a FIB member, you can read the report on FIB's homepage for free. And you can see all the references and all the background that has been provided. This ends chapter 13 on costs, and we continue with chapter 14, studies on the SFTB. Now, studies. I would imagine that a lot of people have dreamed about this type of crossing. It doesn't take more than a boyfriend or a girlfriend on the other side before you start dreaming about things like that. You probably recognize the difference between those dreams and what you have heard here today. But bear in mind that the concept of the SFTB is simple. It becomes complicated because you want to go deeper into the details for reasons of safety and finance, and because there are many elements involved, it seems complicated. Now, this is predominantly from the report. I hope you can share with me that people have dreamed of crossing straits. We have not been able to report of those dreams. We have only been able to report on studies that have been documented and that has been publicized. For subsea rock tunnels, the depth of the crossing is a major factor determining the length and hence the cost. The low cost per meter is partly or fully offset by the length, which for a steep gradient of 8% can be 5 to 10 times the width of the fjord. For more gentle and comfortable gradients, the length and cost of the subsea rock tunnel would increase significantly. And there is a time element here as well. This is another reason for people dreaming about SFTBs. And as Ariana told us this morning, the concept of the submerged floating tube bridge was conceived already in the 19th century, 1886 to be precise, and that is 135 years ago. And then subsequently, there were several other patents that we have included in our bulletin. The largest challenge for the construction of the SFTB in the 1950s, and this is important, was a lack of technology. Especially for the tether structures connecting the bridge with the seabed for deep crossing and for the marine operations. Knowing all the development within the marine discipline and the construction of marine concrete structures that have happened the latest 50 years, we have a totally different background for realizing SFTB now than we had then. In 1969, when the Commission started evaluating the feasibility of the SFTB, the first oil was found in Norway. The technology related to the construction of the oil and gas platforms grew rapidly, and in the early 80s, the first TLP platform was constructed in Scotland. And in 1990, we had one also in Norway. You have seen pictures of this. And the interest around the SFTB grew in those years, together with the technological development. In 1982, Selmer, a contractor, designed and realized the submerged floating rectangular bridge with the length of 600 meters. You've seen pictures of this, to protect two gas pipelines and bridge subsea topography. This structure can be considered as the precursor of the SFTB. We have done many studies in Norway, and there has been many studies performed in lakes in Central Europe, at least that I know of. And there are different reasons behind the interest in studies on the lakes compared to Norway. In Norway, we have some topography and geography that makes it sometimes almost necessary with the SFTB. In the beautiful Central European lakes, there are some other stakeholders. Important also is that in 1986, we arranged the first straight crossing conference, and in 1998, a project and some tests were performed in a study for the Høgsfjord in Norway. In 2000, a study was done for the Lugano Lake in Switzerland, and in 2004 for the Xiandao Lake in China. More proposals were done around the world, but no one of these structures were ever built. I think I would like to give credit to the Norwegian Road Administration for being so, shall we say brave to go in the forefront of this. We need those solutions in this country, but it takes also some guts to go all in. We have heard about studies, Sognefjord and other places, Bjørnafjord, and a lot of efforts has been put into these studies to learn more and to make sure that the risks are acceptable. We have heard about the Söderström tunnel in Stockholm, and we have heard about, and no, we have not heard about SFT across the Golden Horn in Istanbul. That is not going further at the moment. And in the last year, several studies are ongoing on the SFTB, especially for long and deep crossings. And some of them are evaluation for use of the structure in a specific crossing. Norwegian Public Road Administration, ARUP, and others. Others are related to research projects like the one in Korea. And it is my belief that the future will see an increased use of the sea for reasons of, among others, space, environment, food, recreation. And for this reason, the SFTB will have a key role in the future traffic system. We have seen this cross-section. Two bridges are not a new thing. We can use this in many contexts, but we may not want to put them in water. This is the Femern that Gordon was talking about, a very, very large Here you have trains as well as cars. We have seen referenced that we have learned and can learn a lot from the construction and installation of immersed tunnels and also of floating bridges. Lately, several people have started looking at the Hyperloop, which in principle is a tunnel and predominantly planned going in air. You need the tunnel to achieve vacuum inside to achieve high speeds. So that's another type of tunnel. May look like this. You will not like to put this in water, maybe. Quite a bit of interest around this because speed is important, time is important. Now, these studies, they are taken directly from the Bulletin 96, and I shall just pinpoint some elements that I think is important for that particular concept and for the selection of it. The upper left is an early Norwegian patent, actually, from 1923. It has a buoyancy element under here. It looks a little bit steep. I'm not quite sure if you should walk or if you should drive. 1948, we planned, or it was a concept for crossing a strait on the west coast of Norway. It was not successful. The Messina we have heard about. Quite a bit of studies have been done there. Here's another Norwegian study, Eidfjord, 1979. This is the same gas protection tunnel that we have talked about. Normally, in that situation, you would build a rock tunnel. That would take care of both supporting the pipes and reach reasonably calm water at 30-meter water depth. But as you know from the oil and gas industry, time is important for financial reasons, and that is why this one was built, to save time. Rock tunnels take a long time to build. Here we have the Lake Como proposal. This one is very special, I think. This is a concept from 1989, suggested by an architect, Snøhetta. This is crossing the Oslo Fjord, and this is the Oslo Fjord, and on this side you have a city. On this side you don't have any people, no one lives there. And at that time we planned an airport on top to the left. The people here did not want a bridge. Here there were no people to care. So the concept is a submerged floating tube bridge on the end where people didn't want a bridge. And then it goes up as a bridge where people didn't care. And because of the airport, this also have lines for railroad with a different gradient. This one Stein Atle showed. This is Lake Lugano in Switzerland. And Lake Lugano is a very beautiful place. And the idea of having a high-speed railway coming rumbling out of the mountainside was not very attractive. So the measure was to just lower the track a little bit so that it went underwater. It is not built. The rail here is called Alp Transit, and they haven't reached this far yet, as far as I know. This one here is has a sort of different anchoring system. This is from China, 1999. This is also from China, 2004. I'm not quite sure if I understand really what this is. You have the tunnel here, and then you have a pedestrian access and a vehicle access. This is the Högsfjord study. 4 Norwegian contractors were bidding for in the competition. Here from 1999, you have a tether anchored concept. In this case, inclined tethers. Here you have a Japanese concept. And Sognefjorden, we've seen many pictures of already. Stockholm Bridge, we've seen many of, and also Bjørnafjorden. This is interesting because this is a hybrid. Here you have a floating bridge over most of the crossing. And then you go in and drive down in this island, and you have a submerged floating tube bridge just crossing here. So this crossing is not very long, and it enables ships to pass over so that you don't have to have a submerged floating tube bridge all the way. Here is another one. No, yes, here we have another one. I think Gordon showed us this. That's from Turkey. And up here, another Norwegian and another Norwegian. You've seen these pictures before. And this is another Swiss Geneva lake that Stein Atle mentioned. The lakes are really very deep, so that's why you can have this column stabilized tubes. So these were the studies, and I hope that you have all enjoyed your day. Take a look at the bulletin. It is very comprehensive. I think whatever you look after, you will find it in there. Ariana has done a very good job putting it together in a clever way and also in record time. So it has been enjoyable to work with it, and I hope you will enjoy it too. Lastly, this is a picture of me in the middle. That's not why I included it. But early this century, I was invited to participate in a Discovery Channel video in the Extreme Engineering series they had. And the video was about a transatlantic tunnel from London to New York. And you should the travel should take 57 minutes. So 2 types of technology, trains in vacuum and submerged floating tube bridges. When they asked, I was a little bit hesitant. I thought this was a little bit too far-fetched. But then they added that the idea was that this may be realized in this century. So then I participated and this film was made. Thank you for your attention.